discuss about discrete time complex exponentials, which are very important to analyze signals which are in discrete time or digital in nature. In both cases, discrete time complex exponentials comes in handy. So just like their continuous counterpart, we can write discrete time complex exponential as xn equal to c into alpha to the power n, where c and alpha are both complex. Now this also can be written as xn equal to c exponential of beta n, where alpha equal to exponential of beta. So now if we take simple positive exponential, just like the continuous case we have seen, the behavior is similar. Similar to continuous. One, if we take alpha to be real. If alpha is real and positive. So in this case, what will happen? If alpha greater than 1, then the power of alpha will always increase. So therefore, it will increase exponentially. Like that. So this is xn. Now if alpha is if it is 0, of course, there will be constant. If it is between 0 and 1, then it will be a decaying signal, because alpha is less than 1. So therefore, positive power of alpha, this n is integer, will continuously decrease. Like say, if we have 0.5, so first one will be, of course, 0 will be 1, and then 0.5 to the power 1, 0.5. I think graph is not proper for 0.5. It is 0.25, and then continuously it will decrease. So it is nature is very similar. Of course, it's continuous time domain, but for alpha negative, then there is a distinct behavior of the discrete time version xn. Xn then oscillates. So it oscillates because for the odd power, actually it will be negative, and for the even power, it will be positive. So therefore,
Hello, sir.
yes,
Sir, like you said that alpha is a complex number.
no, alpha is positive. Alpha is a real number. Alpha is real.
So, but
Alpha is negative.
So you took alpha to be e power beta. Then how can alpha be negative if it is an exponential?
Yeah, because it is alpha to the power n, no? It is alpha to the power n. Xn equal to alpha to the power n.
Yes, sir, but you
Yeah,
took alpha to be e power beta.
say minus 0.5 to the power n. N equal to 0, 1, 2, like this. So therefore, this will continuously decrease, but oscillates.
Case of alpha is negative, the e power beta representation that we did would not hold.
No, we have not gone to e to the power beta. We have taken the first case,
Okay, sir.
alpha to the power n. Okay, so this is alpha to the power n. Alpha is real and positive, so these two cases, and then we have alpha is negative and real, so xn oscillates.
Excuse me, sir.
Yes,
So can you please repeat that part? If alpha is negative, then xn oscillate
yes,
for
alpha
odd
is
and
negative, so minus 0.5 to the power 0 will be 1 here. Okay, then minus 0.5 to the power 1 is minus 0.5 here. Okay, then minus 0.5 to the power 2 is 0.25 here, and minus 0.5 to the power 3 is minus 0.0625. So therefore it will oscillates, because this is nothing but minus 1 to the power n into 0.5 to the power n. Okay, so that minus 1 to the power n we can bring out. So obviously it will oscillate corresponding to n become odd or even. So this is a new characteristics that has come into picture because of the discrete case. In the discrete case, the n becoming an integer. There can be also divergent sequence. So this is of course minus 1 less than alpha less than 0. And if we have alpha less than minus 1, So value of that will be interpreted minus 1 to the power n into alpha to the power n. Alpha is greater than 1, so the value magnitude will continuously increase. Sorry. So this is basically 0, then this is 1, this is 2, this is 3, 4, like that. So because mod of alpha is greater than 1, so therefore the magnitude is increasing, and because there is a minus sign involved, so a minus 1 to the power n is multiplied, which is basically giving rise to the oscillation. Now we can discuss about discrete time sinusoidal signal. So that can be obtained from that basic relation C exponential of beta n so imaginary beta n is integer. If beta is imaginary, then mod of exponential of beta is equal to 1. Because we are interested into a sinusoidal signal, so let us take xn equal to exponential of j omega naught n, which is analogous to our continuous counterpart. When we analyzed sinusoidal signal, we have taken exponential of j omega naught t. Okay, so similar to that, here we are taking exponential of j omega naught n. So this is of course cosine of omega naught n plus j into sine of omega naught n. So we can take either cosine or sine signal. If we take a cosinusoidal general signal like a case a cos omega 0 n plus phi, so this can be written as a by 2 exponential of j phi exponential of j omega naught into n plus a by 2 exponential of minus j phi into exponential of minus j omega naught n. So this mod of exponential of j omega naught n does not give rise to any change in the amplitude, because that is equal to 1. So which gives finite power but infinite energy. So therefore this a by 2 term and exponential j phi term is basically gives rise to the modulation. So now let us put it in the previous case we are taking as alpha. So we will put C equal to C exponential of j theta and alpha equal to mod alpha so both like previous case we are taking both the exponents. So in that case C alpha to the power n would be mod C into mod alpha to the power n cosine of omega naught n plus theta plus j mod C into mod alpha to the power n sine of omega naught n plus theta. So in this case also we will see that oscillations comes into picture depending on the value of alpha, either it will be converging or diverging. Depending on the value of alpha, this will either a damped sinusoid or a exponentially diverging sinusoid. So because this alpha term, of course, we cannot call this signal exactly periodic, okay? So it will be, as per definition, the values need to be same at every period. So that will not be satisfied because of this value of alpha. If it is equal to 1, that will be satisfied. In either for greater than 1, it will be diverging, and for less than 1 it will be converging. So this is for, say, alpha greater than 1. Similarly, if it is alpha less than 1, it will converge. Now, of course, this is simple to understand. The one most important thing that is again different about the periodicity of discrete time exponential. So we have seen in continuous time case that if we have omega naught, and there would be harmonics of omega naught can also be present, and the combination of omega naught plus its harmonics all are basically combination is periodic. And if we increase omega naught, so in that case actually the period will decrease, so its harmonics will be created thereby. Now in the discrete case, however, if we take xn equal to exponential of j omega naught plus twice pi into n, so then it becomes exponential of j twice pi n into exponential of j omega naught n. So this is nothing but exponential of, because n is integer, so this is nothing but exponential of j omega naught n. So exponential of j twice pi n, exponential of j pi n is equal to minus 1 to the power n. So therefore exponential of j twice pi by n is equal to 1 to the power n equal to 1. So there is a very important conclusion comes from this observation, is that unlike the continuous time sinusoids, discrete time sinusoids are unique only in a principal interval. Interval of say 0 less than equal to omega naught less than equal to twice pi. So the moment omega naught crosses twice pi, or of course we can other way also write both sides symmetric fashion, minus pi less than equal to omega 0 less than equal to pi. So this interval in the digital domain is known as the principal interval, and we shall see later that all the discrete time transforms will be unique only in the principal interval. So now considering definition of periodicity, exponential of j omega naught n plus small n is the variable and capital N is the period, should be equal to exponential of j omega naught n for periodic signal. So therefore either exponential of j omega naught n or no, sorry, not either. In this case, therefore, exponential of j omega naught capital N equal to 1. Okay, or otherwise omega naught need to be equal to 0. So in that case, of course, periodicity is undefined. So in that case, of course, this relation will be satisfied. Okay, this is satisfied either for omega exponential of j omega naught equal to 1 or omega naught equal to 0. Satisfies this relation. Now omega naught exponential of j omega naught n equal to 1. So with our previous observation, we can tell that n is multiple of multiples of twice pi. Okay.
So whole omega naught n will be multiple of 2.
N is multiple of twice pi because we have here omega naught plus twice pi into n, small n. So this twice pi into small n is an integer. Okay. So that way we are adding it omega 0 into small n, we have make it separate. Okay. So therefore that integer multiplied by twice pi need to be satisfied. So that is equal to this capital N. Or omega naught n equal to twice pi m. M is an integer.
Sir, n is multiple of 2 pi or sir 2 pi by omega naught?
No, it is twice pi.
So that will be e to the power j
No,
omega naught
because
2 pi.
here, no, we are satisfying omega naught exponential of j omega naught equal to 1. Okay. So that is equal to exponential of j twice pi n. That is exponential of j twice pi n. So that n is also integer. So similarly, therefore, that n we are writing in a different index. That omega naught n is nothing but twice pi into m. That is m is an integer, similar to the previous case where small n was an integer. All right. Or
It is not necessary for capital N to be an integer.
capital N is multiple of twice pi, integer multiple of twice pi. Yeah. N is a capital N is also integer.
If capital N is an integer, then it cannot be a multiple of twice pi, since pi is an irrational.
Omega naught n is equal to, yeah, that need to be satisfied. So that we will write next. Okay, what you were telling. So omega naught by twice pi is equal to m by n. Okay. Now, if that is not an integer, so then what it has to be? Both has to be integer. Okay. Or so this has to be a rational number.
Sir, omega can also be an integer.
Omega can be also be integer. That is up to our choice. Okay, omega can be an integer, but in that case, of course, uh, it will not maintain periodicity for more than 2 samples. If omega is integer, only 2 samples, it will oscillate continuously if omega is integer. All right. So what will happen if omega is integer? So omega is also integer and this n is also integer. So integer m plus twice pi into n. So therefore that if I say exponential of j twice pi n equal to 1, and if it is an integer exponential of j to some integer, all right, omega 0 would be some integer value into n exponential of jn.
So I didn't understand this part. So we're writing e to the power j omega naught capital N is equal to 1. That means that omega naught n should be 2 pi or 2 pi m. So why we're writing n is multiple of 2 pi? So capital N, how can it be multiple of 2 pi? It has to be multiple of 2 pi by omega naught, right?
So omega naught n equal to twice pi by m, twice pi m. So n is equal to twice pi m by omega naught. Okay.
Yes, sir.
No, sir, it's talking about the line.
So multiple of 2 pi by omega naught. If it's multiple of 2 pi, it will become like
Yeah, okay,
4 pi
okay.
square by t or something.
Yes, 2 pi by omega naught. So we can also write that if xn is periodic, say with a fundamental period of capital N, its fundamental frequency would be twice pi by capital N, and therefore twice pi by n is equal to omega naught by m. Okay. So basically, why discrete time? This is, important to understand, because suppose I take certain omega naught, maybe 1 radian per second, or 2 radian, or 10 radian, something like that. But then I have to also fix sample that continuous time signal, and corresponding to the sampling rate, I will have an integer number. Okay, if the sampling interval is not at the integer multiple of that omega naught, what will happen? This we will not get a particular periodicity with respect to an integer n. All right. So it depends that I have a continuous time signal. Okay. Now I am sampling. Now suppose if I sample like that, that is an fraction of that omega naught. Okay. So that sampling frequency is integer times that omega naught. Then what will happen? It will exactly cross here. So therefore, we will observe the periodicity. We will observe the periodicity. But suppose I do not sample like this. Sorry. I do not sample exactly at the integer multiple, so I am here. So then what will happen? It may happen that because this point and this point, the location may not be at the multiple of this omega crossing. Okay, so it may not be periodic. It will be periodic. It will be periodic at after certain interval, but depending on that that whether we satisfy this relation that the discrete sequence xn is a period of n. So that means after capital N number of sample, okay, it will repeat itself. That need to be satisfied in the discrete domain. So it is not sufficient that I have a sinusoid and I have sampled at an interval. So then I will get always a periodic signal in the discrete domain. It will be, of course, periodic in the sense that it will repeat, but because that next after capital T time, actually the the sample may not be same, because this is capital T. So this interval may not be equal to this interval. So therefore this periodicity will not be satisfied. So to satisfy this periodicity, we have to satisfy this condition apart from taking a sinusoidal signal in the continuous time domain. So we can summarize this observation. In the continuous and discrete domain. Continuous time, it could be any other variable. Now, generally in this course, of course, we are considering time, and we shall see certain properties are unique with respect to time, which are not required if we take any other variable. So in the continuous time, we write exponential of j omega naught t. In the discrete domain, we write exponential of j omega naught into n. So it is distinct for distinct omega naught. Okay. If it is in a harmonics, of course, it will repeat itself in the original period as well. So therefore, if omega naught is distinct, then this one, this xt is also distinct. Now here, of course, it is not so. Signal is identical for values of omega naught separated by multiple of twice pi. So here, suppose I have 1 radian per second, 1 radian, and then I add twice pi. Okay, so that is twice pi by 1 into t. So that is a distinct sinusoid. But here, if we add twice pi, so actually that will not be distinct because of the observation that we have seen. So here fundamental frequency omega naught. Here fundamental frequency. Omega naught by m. And then you understand, because m is an integer, if this is not rational number, okay, then you may not get a defined fundamental frequency. This is periodic for a choice of omega. This is periodic only if omega naught equal to twice pi m by n. Okay. Fundamental period is twice pi by omega naught. Fundamental period m into twice pi by omega naught. In both cases, of course, omega naught not equal to 0. There are some other observation that this can be periodic with integer or real. Here it has to be an integer. Period can be only integer. So some example were given in the book. Say xt equal to cosine of twice pi t by 12 and xn equal to cosine twice pi n by 12. So these as both have period 12. the second example that has been given, xt equal to cosine of 8 pi t by 31 and xn equal to cosine of 8 pi n by 31. So this has period 31 by 4. However, because here the period n can be integer, so the period is 31. So that is because of that consequence of sampling, and we can move only in the integer space in case of xn. With these few observations, we will next go to some unit impulse and step function. So discrete time case is easy because here we can define unit impulse and step easily. Delta n equal to 0, n not equal to 0, 1 for n equal to 0. So that is the impulse function. The step function un is equal to 0 for n less than 0, 1 for n greater than 0. So this is unit step. Now very easily one can express delta n in terms of a discrete approximation of the differentiation, that is the backward difference, un minus un minus 1. And un is be the reverse because it is basically delta n is related to un through differential operator. So therefore this will be the summation n equal to minus infinity to n m equal to minus infinity to m delta n. So one can of course shift the delta function by applying shift, and similarly the step function also can be shifted applying the rules of shift. However, delta function has an important property has the property of sampling. Or picking up a particular M. So if I have a signal xn, when multiplied by delta n, because delta n equal to 0 other than n equal to 0, so this will be x0 multiplied by delta n, whatever the value of x0, so which is nothing but equal to x0. Similarly, if we have shifted delta n by say n0, then we have x n0 into delta n minus n0 equal to x n0. So basically, we shall see later that we can model sampling of a signal through the delta function. So though in the discrete domain it was easy, continuous domain is not so easy. Continuous domain step function is easy to write. Ut equal to 0, t less than 0 equal to 1 for t greater than 0. So which in essence is a discontinuity at t equal to 0. This is the unit step. Now continuous time delta function is related through to the step function through that integration relation or through that differentiation relation. So that we shall discuss next step.